Okay, so your bellwether question is about ionic and covalent bonds. Covalent bonds involves the sharing of electrons, so you'll just want to write that down. And ionic bonds don't involve sharing, instead they involve the word transfer of electrons. So two key words: ionic, transfer of electrons; covalent, sharing of electrons. And that's going to be the rest of this chapter. We're going to be talking about how that happens, how to tell the difference between the two, what kinds of properties are different between those two things when they happen. Okay, so today's question said, explain the difference between ionic and covalent bonds. Ionic bonds involve the transfer of electrons, and covalent bonds involve the sharing of electrons. Put it as simple as that, that covers it. And I want you to know that. I need to take the hat off for class. Thank you. Okay, put your bellwork books away. I want to talk briefly about yesterday's quiz. Yesterday's quiz is graded, and it's not, I just noticed that I didn't enter yours in the portal yet. They're done. I just need to punch them into the portal. They were not very good, and it wasn't because of the questions, because I went through all the questions. They are all straight out of the notes from Monday and Tuesday. I'm going to encourage you. You need to study, okay? And that means on an ongoing basis. It's not just when we have a test. Please run this way. Not just before a test. You should every night be doing a little bit of reviewing of that day's notes. That's the best way you're going to stay up with this class. I do give a lot of notes, and you figured that out already. Go back and review those, because yesterday's quiz was multiple choice questions from the notes. And there's nothing much easier than multiple choice questions. So which of those four things was not a property of chlorine gas? Okay. You should have been able to figure that out if you had paid attention in class, taken some notes, and reviewed that the night before, because I do give quizzes every Wednesday and every Friday if we're not having a test, which means we have another quiz tomorrow. Okay, and so you'd be well advised to study what? Everything we've talked about since Monday at this point. Okay, so Monday, Tuesday, Wednesday, Thursday are free game for Friday's quiz. I'll never go back to the last chapter unless I tell you ahead of time, okay? But anything up into, including today's notes, could show up on tomorrow's quiz. Okay, so be prepared for those things. I'm not going to go through the quiz with you because the answers are in your notes or in the textbook. Everything that I gave you for notes is from the textbook as well, and that's on the properties of reactants and products. Okay, take out your notebooks. I want to teach on ionic bonds today. Remember a couple days ago we talked about how do things stick together? I think it was Monday's bellwork question. And we talked about everything from zippers to Velcro to Gorilla Glue to duct tape. We had a whole list. Well, that's not how atoms stick to each other. There's basically two ways that atoms are going to combine. And that's either ionic bonds, which we're talking about today and probably tomorrow, and then covalent bonds, which we're going to talk about after that. Okay? And I want you to understand, Brent, not just the names and that involves sharing or transfer of electrons, but I want you to understand how this happens. So today, when we talk about it here, I want you to be able to draw some diagrams, show me how the electrons are moved from one atom to another. I want you to understand why that happens. I want you to understand what the mechanism is that means that they're going to stick together. Okay, and this is called ionic bonding. So I'm going to give you a few notes here. Then at the end of the class, we're going to work some problems together on the smartboard here to illustrate that. And I want you to know how to do that. The reason I'm recording this for those who aren't in this class right now is because this is an incredibly important lesson that's going to be important for the rest of the school year. Okay, so let me encourage you. Take some notes, pay attention, and know how to do this. So, how elements form. Today we're talking about ionic bonds. We already talked about this week, so I'm going to jump ahead here. We're going to look at the rest of the chapter. It has to do with either ionic or covalent. And again, today we're focusing on ionic bonds. What is an ionic bond? What is an ion? We'll cover that first. Okay, two things we need to talk about before we talk about ionic bonds in particular. How do chemical reactions form? And so I want you to write down that the first thing that has to happen before a chemical can react with another chemical is they need to bump into each other. That's what that word means right there, a collision. Okay? And it's the same way in life. I use a lot of analogies in class, and I talk about atoms as if they were people because it's more relatable that way. And so again, you're not going to react with somebody unless you get close enough to talk to them, close enough to interact with them, close enough to have lunch with them, okay? And the closer you are and the more you bump into somebody, the better you get to know them. The more time you spend with somebody, the better your relationship, whether that's a boyfriend-girlfriend, a husband-wife, a mother-father, father-daughter, mother-daughter, whatever the case may be. Collisions. And again, I'm not talking about personal collisions with people, but I'm talking about spending time close to people. Same thing happens in chemistry. Atoms can't react unless they bump into each other. What does that mean for us? That means I can't have two gases in two separate test tubes react with each other unless I take the stoppers off and mix them together. I can't have two liquids form a new compound unless I pour them both into the same beaker and stir them up. I can't have two solids react with each other unless I take those two solids and grind them up together, sort of using a mortar and pestle, kind of like this, and grind them together and let them interact, let them react with each other. Okay? The second thing that we need to know is that chemical reactions only involve the valence electrons. Remember, the valence electrons are your outer shell electrons. Nobody, for the rest of the school year, we will hardly ever mention protons and neutrons again because they don't react. They do not get involved in chemical reactions. It's important that you know they're there. It's important you know that they account for the positive part of an atom, but they don't involve themselves in chemical reactions. So it's only those outer shell electrons, 1 through 8, on the outer energy level that are going to interact. And it'll be obvious why. If two atoms are bouncing into each other literally like this, it's only the outside ones that get to meet each other. Okay, it's like when two cars bump into each other, the only thing that should meet first anyways is the bumpers. That's why they're called bumpers. Okay? Cars today are designed, by the way, to handle up to 5-mile-per-hour collision and just damage the bumper without damaging the rest of the vehicle. Well, the 5-mile-per-hour bumper, whether it's efficient or effective or not, remains to be seen. Okay, the next thing we need to know is that those valence electrons are going to interact with each other to try and fulfill what we call the Octet Rule. We talked about that on Tuesday, I think, for Bellwood. The Octet Rule states that every atom wants to be like the noble gases, wants to have 8 electrons. Okay? Things that are stable are going to not react, and things that are not stable are going to react. So each noble gas has 8 valence electrons, except for helium. Helium, remember, is the exception. Helium is going to have only 2 because it only has 2 electrons. Now, what else do we know about these noble gases? Remember, these are the guys that they don't need to interact because they've already got everything they need. Every chemical reaction is going to take place in order to try and fulfill the Octet Rule for all the atoms. Every atom wants to go live in the castle with the nobles. They want to go to the parties. They want to have all their food taken care of. They want to have the luxury that the nobles have. And so they're always going to be trying to satisfy their outer energy level so that it has 8 electrons. If they can get 8 electrons, they'll feel like they're part of the noble class. And they will be stable. They will have that stability that comes with having all of their needs met. Okay, so here's the Octet Rule. And again, achieving that configuration is the goal of every atom. Atoms collide with enough energy, the electrons will rearrange, and we will have a new compound. We will have a chemical reaction take place. So this is the method by which this all happens. Let's define an ion. Okay, first, what is an ion? We need to know this before we start talking about ionic bonds. An ion is an atom or group of atoms that has a charge. A charge means an electrical charge, either negative or positive. And it gets to be an ion by either losing or gaining electrons. I'm going to give you an example on the whiteboard here. Okay, so an ion. Ion is no longer a neutral atom. An ion is an atom that has either gained or lost electrons and become either positive or negative. Okay, let's talk about chlorine. Chlorine is our classic example here. Chlorine, if I just look on the periodic table, we learned how to do this in chapter 2. Its atomic number is 17. So if I ask you how many protons it got, everybody tells me 17. How many electrons does it have? 17. So that's chlorine as an atom. Now, for chlorine to become an ion, we're going to just look at its Bohr diagram, which I've already drawn here. Its Bohr diagram shows that it has 2 plus 8 plus 1, 2, 3, 4, 5, 6, 7. 17 electrons means how many in its outer energy level, Rodney? 7, good. Everything in group 17, everything in that halogen group is going to have 7 valence electrons. That means, how many does it need to be like a noble gas? Needs 1 more. Okay, so I'm going to draw a little box up here, and that's kind of like the empty spot in the soul of a halogen, okay? It just needs 1 more electron, and it can be like the noble gases. It's got that 1 empty spot, sort of like an unsaved person, got an empty spot in their heart where Jesus needs to be. But there's an empty spot in a halogen's life, and it's not for Jesus, it's for an electron. He is unhappy. All these halogens are extremely reactive because they are unhappy until they can fill that last spot with 1 more electron. So what happens is chlorine is going to hunt around until it bumps into somebody that has an electron that it can steal. And I'll talk about that in a second. If chlorine happens to pick up an extra electron, here's what we get. It's still going to have 17 protons, because remember, if I don't have 17 protons, I am not chlorine. But if I pick up an extra electron and put 1 here, right here, it now has 18 electrons. And 18 negatives and 17 positives adds up to what? 17 and negative 18? Negative 1. And so chlorine is going to pick up 1 electron. It's going to become a negative 1 ion. I've gone from a chlorine atom to a chlorine ion by gaining 1 electron. Chlorine is no longer balanced as far as its charges. It's got 17 protons and 18 electrons, but now it's happy. It's very stable like this. Chlorine is a very stable atom once it becomes an ion. In fact, a chlorine ion is more stable than a chlorine atom. Let's talk about sodium on this side. Here's sodium, atomic number 11. As an atom, sodium is going to have 11 protons and 11 electrons. It's going to be perfectly balanced. And if I draw the Bohr diagram for sodium, you'll see it's got 2 electrons in its first energy level. It's got 8 electrons in its second energy level, but that only adds up to 10. We know it has 11 because its atomic number is 11. So we add a third energy level, and it's got that 1 little electron out there in the outer energy level. What is different about that last electron than the other 10? It's lonely, okay? It's all by itself. And just like if I asked you about a bunch of sheep out in the wilderness and which one is the wolf going to pick off, he's usually looking for what? The one by itself, the one that's wandering away, not paying attention, not sticking with the pack. So the one by itself, that last little electron, really is so far away from the nucleus. Literally it is, because it's got the highest energy level. It's the farthest from the nucleus, which is where it gets its attachment from. Remember, positives in the nucleus and negative electrons are attracted to each other. That's what holds the whole atom together. But that last little electron has the weakest attachment to the nucleus. It's all by itself. It feels left out, maybe, if you want to think of it as a person, okay? It's either going to do one of two things. It's either going to run away from home, okay, and find somebody else who wants to love it more than it feels like sodium doesn't love it anymore. Or somebody's going to come along and snatch it. It's going to be kidnapped, okay? Some other atom who has a desire to steal little electrons from other atoms is going to come along and steal that electron. Now, whether you want to think of it as losing an electron or somebody else stealing that electron, what happens is this electron leaves. And when we lose that one electron from sodium, again, I do no longer have an atom. I have an ion. Because now I've got 11 protons in the nucleus, but only 10 electrons. And if I have 11 protons, that's 11 positives, 10 electrons, which is 10 negatives. And what's positive 11 and negative 10, Maddie? 11 minus 10, 1. And so that means sodium becomes a +1 ion. This is how ions form, either by losing their outer shell electrons or by gaining their outer shell electrons. Now, as it turns out, that little electron that sodium just lost, look at his outer shell now. How many are in his outer shell, Max Dennis? Yeah, he lost that electron and he don't even care because he's happier without it. You know how Jesus chases after the one lamb and leaves the 99 behind? Sodium's not like that. He's completely selfish. He'd rather keep his 10 and ignore that one that ran away. Okay? He didn't give a rip about losing 1 or 2 electrons. Because they're so far away, he doesn't even miss it. He's happier without it. So sodium is very stable as a +1 ion. Chlorine is very stable as a -1 ion. And if they get together close enough, I get +1 sodium and -1 chlorine. And what do positives and negatives do? Attract or repel? Exactly. They don't.
Attract.
They attract. Good. Opposites attract, okay? So positives and negatives would be electrically attracted to each other, and they would stick. And that's a very strong bond, and that is what we call an ionic bond. Now, it just so happens that sodium loses that electron. It actually is the same electron that ends up over here with chlorine. And what we have seen is a transfer of electrons from sodium to chlorine. In the process, we create 2 ions, a positive one and a negative one. And when I get positive and negative ions in the same space, boom, they stick to each other because of electrical charges. Good. Excuse me, I need to find something. Throat. Coffee. Okay, so ions, everybody got it? So we form charges, positive and negative. That means our ions are not going to have an equal number of protons as electrons anymore. So you need to be careful if talking about atoms or ions. And ions form when valence electrons are rearranged from one atom to another. Now, there's 2 types of ions. I want you to know these 2 terms. I've written this word out because it's very easy. If you write out cation with a giant T in the middle,
It's a plus sign.
it's a plus sign. Good. And I do that. I've done that for years to remind me because I always got confused. Which one's the positive one and which one's the negative one? If you write cation in your notes like this with a big super huge T that looks like a plus sign, you'll always remember cations are positive and the anions are going to be the negative ones. I don't have any way to remember that other than it's the other one, okay? If cations are positive with a big T in the middle, then anions are going to be the negative ones. Maybe N for negative, because it's got an N right there as the second letter. You come up with a way to remember it, you gotta remember it. So here, this one is an anion. Sodium over here is going to be a cation. Positive, cation, negative, anion. And this. Now you're going to see a pattern start to emerge. Remember the bell work we did yesterday where we took all of the group 1s and all the group 17s, and we came up with 42 different combinations. Remember that? Okay, what we were doing was taking cations, plus ones, and anions, minus ones, and combining them, just like sodium and chloride here. Now, one thing you'll notice, every time we do this, for ionic bonds only, we're always going to have a metal, that's going to be your positive one, and you're always going to have a non-metal, that's going to be your negative anion. Always. And when we get to the end of the chapter, one of the things you're going to have to be able to do is, if I give you two elements, you're going to have to tell me, is it going to form an ionic bond or a covalent bond? So ionic bonds are always going to be a metal, something to the left of the staircase, and a non-metal, something to the right of the staircase. Because metals only form positive ions, and non-metals only form negative ions. When we get to the covalent ones, they do something completely different. Different mechanism, different rules, different criteria. Okay, so two types. Ionic is always going to be a metal and a non-metal, or something from the left side of the periodic table, something from the right side of the periodic table. Whoops. Yeah. Okay, I'm going to jump here to another screen on my whiteboard. Back up here. I want you to write down these 4 rules right here in your notes. And this is a procedure I'm going to teach you on how to draw a chemical reaction for an ionic bond. So the first step, and we'll go do a couple problems after you write these down. Number 1, draw the Lewis dot diagram for each reactant, okay, each of the elements. So step number 1, and please number these in your notes, put a big box around it because you're going to need to remember these steps. Number 1, draw a Lewis dot diagram for each reactant. I've abbreviated diagram for diag here. Number 2, show how the electrons transfer from a metal to a non-metal, or you could say from the cation to the anion, or you could say from one element to another element. We're going to draw some pictures here. Jordan, you going to be able to do this tomorrow on the quiz? Okay. Brent? You need to know these steps, okay? Number 3, we will add more atoms to our picture if we need to. And I'll show you how that works. And then number 4, I'm going to write the final formula for the reaction. I got those down? Zach, I don't mind you sitting in back there, as long as you're not throwing things through the hoop. Yes, sir. Okay, how do we use those 4 steps to solve one of these problems? Let me give you 2 elements, and then we'll walk through it. Let's write down magnesium on the left-hand side and fluorine on the right-hand side. Okay, I'm asking you to kind of figure out, how does magnesium and fluorine combine in an ionic bond to form a compound? Step number 1, write or draw the Lewis dot diagram. Who wants to come up here and put the electrons around these guys? Emma, come on up. And put the number of electrons around each of them that is appropriate. I've already changed it to red, so it'll show up nice for the electrons here. I don't want the circles, I just want the Lewis dot diagram, so you're just showing me the dots, just the dots, yeah. Thank you. Okay, good. So we got magnesium in group 2. We look at the periodic table, magnesium's in group 2. If I was going to draw something like this, we would find out it has 2 valence electrons, but we know everything in group 2 has 2 valence electrons. For fluorine, fluorine's in group 17, and we should know that everything in group 17 has 7 valence electrons, or 1 less than the noble gases. So 1, 2, 3, 4, 5, 6, 7. So step 1, draw these are called the Lewis dot diagrams. Okay? Number 2, we're going to show how the electrons move from here to there. They're getting either transferred, or you can think of it as stealing or running away, whatever you want. The electrons move. What I like to do is put a little box over here to illustrate. Fluorine's got 7, and it's missing 1. It needs that last electron to be happy, that last electron to be stable. It needs that last electron to be like the noble gases. So we're going to sort of circle one of these electrons, draw an arrow, and say, ha ha. That electron from magnesium is going to end up over there for fluorine. Fluorine's going to have 8 electrons. He's going to be very happy, stable. The problem is, magnesium's not happy yet. How do I resolve this situation?
Write down and see.
Rodney?
Write down and see.
How? Zach? What do I do with this electron? Magnesium's not happy. What do we need here, Max? I need another fluorine. And that's not a problem, because where there's one fluorine, there's trillions of fluorines. Remember, in any given drop of something, there are trillions of atoms. If I got 2 magnesium and fluorine interacting, there's definitely more fluorine laying around. Okay? And every fluorine is going to have those 7 electrons, like Emma drew, and it's going to be missing 1. So I got another fluorine next door. Okay? There are literally trillions of these things in one drop. So again, we don't need to go looking for more. There's plenty of them laying around. So this electron is going to go over here. There we go. Now is magnesium happy? Yes, magnesium has now lost 2 electrons. So what is his ion going to look like? He's going to be magnesium with a what charge here? If he lost 2 electrons, he is... I didn't hear what you said.
Yeah, you right.
No? If he has lost 2 electrons, he's lost 2 electrons. Emma?
It's a positive. Positive 2.
Positive 2. Okay, think about this for a second. Okay? Let's think about this for a second. Magnesium is number 12. It has 12 protons and 12 electrons. But he lost 2 of the negatively charged electrons. Okay? That means what's left over is positive. He's got 2 more protons now than he does electrons. So you always got to stop and think about this. If I'm losing electrons, I become positive. That's the magnesium here. And he lost 2 of them, so he becomes plus 2. Fluorine, on the other hand, over here, each one of these fluorines has gained 1 electron. So each of the fluorines is now a -1 ion. Cation, anion. What I'm showing in my picture, though, is that I actually have to have 2 of these. So my final formula is Mg F with the subscript of 2. Magnesium fluoride is what we call it. And it's a ratio of 2 to 1. We didn't do anything like this on yesterday's bell work We just did the one-to-one, one group 1 and one group 17. But this one's group 2. So you're going to see if I take anything from group 2, like magnesium, or calcium, or beryllium, or strontium, or any element from the halogens, it's always going to be a 2-to-1 ratio like this. I could have MgCl2, MgI2, MgBr2. I could have calcium, CaF2, Cl2, CaI2, CaBr2. I could go to beryllium, BeF2, BeI2. Does everybody see the pattern here? Because the number of valence electrons is always going to be the same for each group. Once you figure out what one formula is, it's going to be the same for every other combination of elements in those groups. Let's do another one. Okay? Let's combine aluminum with bromine. Anybody want to come up and put my electron dots here? Aluminum, bromine. Come on up, Seth. Good. Bromine, number 35. Good. Perfect. Okay. So Zach says, okay, aluminum is in group 13. It's going to have 3 electrons. Bromine is in group 17. It's going to be just like chlorine. It's missing 1 right there. Okay, so we're going to start moving electrons around. So let's move one of these electrons here into that box right there. Bromine is now happy. He's got 8. Yay! How about aluminum? Nope, not yet. What can I do? I gotta help aluminum out here. Jordan?
Add 2 more.
2 more? Okay, you're right. So we actually have 2 more electrons to give away, but each bromine can only take 1. So what Jordan says is right. I need to add 2 more bromines, each which has 1, 2, 3, 4, 5, 6, 7 already. 1, 2, 3, 4, 5, 6, 7 already. Each of which is missing that last electron for its outer shell to make it have the 8. Okay, so we're going to take our electrons here from aluminum, we're going to deliver one to him, deliver one to him. We have a transfer of electrons taking place, which tells us it's an ionic bond. What is my aluminum ion going to look like? Max? Positive 3, okay, because we have lost 3 electrons, which means I now have a plus 3. I have 3 more protons than I ended up with electrons. Okay, and we're going to combine that with 3 bromines, each of which is a -1 cation. Each one of these becomes -1 because they've gained 1 electron. And what's my final formula going to be? Zach? Kennedy? AlBr3, and we draw that like this, Al, and then the capital B, small r, and then a small 3 for the subscript. 3 bromines, 1 aluminum. AlBr3, aluminum bromide is what we call it. Okay, everybody getting the hang of this? Okay, we're going to go to a tricky one here. This is about as difficult as they get. I'm going to give you aluminum again. And we're going to go with oxygen. Question. I'm going to have somebody else do it this time. Who wants to put some electrons up here? Carly, you want to put some electrons up here? Gordon, you want to put some electrons up here? Max, come on up. I know you can do it. 6 electrons because it's in group 16, okay? And we're going to put a couple little boxes over here. It's missing our 2. I'll put a little box up here and a little box down here. It needs 2 more electrons to be like its noble gas neighbor, okay? It's got 6 electrons, wants to have 8, so we need 2 more. Okay, let's switch back to my green. Let's deliver some electrons and see if we can make everybody happy. Aluminum doesn't care about these 3 electrons. They're way out on the outside of it, okay? So one of them runs away from home, goes over here. And the other one runs away from home and goes over here. Okay, that oxygen is now happy. He's got 8 electrons, but aluminum, he's even more frustrated than he was now, okay? So I got rid of those 2 troublemakers, but I still got 1 stuck here in my outer shell. And that's bothersome. How can I resolve this situation? Jordan?
You gotta add 1 oxygen. You got 2 oxygen.
Okay. He's right. He knows where I'm going with this, but let's do it one step at a time. I need to add another oxygen, okay? Because I need more places to put some electrons. So let's move this electron here over there. But he's still got 1 more space. So what? Now I need another aluminum. Oops. Sorry about that. So I need another aluminum over here. So we add another aluminum with his 3 electrons. 1, 2, 3. And we'll take this guy right here and put him in that box. That oxygen is now happy. But now aluminum's got 2. So we go back to the other side and say, need another oxygen. Okay? Add his 6 electrons. 1, 2, 3, 4, 5, 6. He's still got 2 empty spots here. 1, 2. And now we have a perfect match. We're going to say this electron goes here. This electron goes here. So what we end up doing, guys, is we go back and forth, adding 1 atom at a time until all of my atoms are transferred and everybody's happy. I've got 2 aluminums over here, each of which has lost 3 electrons, so I got 6 electrons lost. Over here I have 3 oxygens, each which needed 2 electrons and has gained 2 electrons. 2 plus 2 plus 2, 6 electrons gained. We didn't lose any electrons, we didn't gain electrons, we just transferred them from this side to this side. I basically have 2 aluminums, each with a plus 3. This is my cation. Reacting with 3 oxygens, each which is now a -2 anion. And my final formula, somebody raise their hand. Kennedy? How many aluminums? Okay, well, the only thing we can change in the formula is the subscripts. So it's going to have aluminum and oxygen. And since I have 2 aluminums, I put this subscript here. And since I have 3 oxygens, I put that subscript there. That's my final answer, okay? Al2O3. Now this is aluminum oxide, more commonly known as rust. Okay, there's your rust on a piece of iron. Al2O3. Okay, it's still metal, non-metal, ionic compound. We're losing electrons on this side, we're gaining electrons on this side. We're transferring electrons. This is what ionic compounds are called. Emma, question? Jordan, question? Okay. Let's do another one. So I should be able to take anything on the left and anything on the right and combine the 2. Let's do beryllium and nitrogen. Who wants to give me some electrons up here? Maddie, you up for this? Give us some red dots. Put some measles on those elements. That's nice. That looks nice.
Yeah, keep it.
Don't take it off.
Show me the stars too.
atomic number is 7, but it's only got 5 valence electrons. 2 in the first shot, 5 in the second. Good. Okay, so we got beryllium, group 2, 2 valence electrons. Nitrogen, group 15, 1, 2, 3, 4, 5. 5 valence electrons, just count from the left-hand side. And so nitrogen here is going to be looking for 3. 1, 2, 3. He wants to find 3 more so he can have 8. Octet rule. Beryllium doesn't want these 2. He's going to get rid of those 2 if he can. So let's start. This guy, I'm going to travel over to here. Beryllium, going to lose this one here. Oops. Beryllium's happy, nitrogen isn't. What do I need? Taylor?
Another beryllium?
Need another beryllium, so let's add one here. Get some more electrons so we can fill up that spot over there. Don't put a B because that's boron. Okay, beryllium, so we're going to have this guy right here. We're using blue now. We'll fill up that spot for nitrogen. Nitrogen's done, but beryllium, nah. Taylor, what do I need now?
Another nitrogen.
Another nitrogen, go to this side. Okay, give him his 5 electrons. 1, 2, 3, 4, 5. We got 3 spots missing. This one spot missing. This spot missing, this spot missing. So take this one, send him over there. Uh-oh. I got 2 more empty spaces over there. What do I need to add here, Max? Add another beryllium, okay, with his 2 electrons. And we're going to draw this guy, send him over there. He's going to transfer, whoops, electrons. And this guy over here. Ta-da! Okay, so now everybody's happy. Beryllium lost their electrons. They are now happy because their outer shell is filled. Nitrogen has gained 3 electrons. They're happy because they now have 8 electrons. So my beryllium has lost 2. Each one becomes a +2. My nitrogens, and I've got 3 of them. My nitrogens have each gained 3 electrons, so they are now -3. And there's 2 nitrogens. 2 nitrogens, each with a -3 charge. And together, they're combining to form BeN, Ben. Okay, and I put my subscripts. How many berylliums did I use? How many nitrogens did I use? So it's Be3N2. My subscripts are Be3N2. So my formula, my final formula here, subscripts are the minimum number of each of the elements that are required to transfer all these electrons. Okay? So this is the opposite one of the aluminum and oxygen one we just did. I've got +2 and -3 instead of +3 and -2. Again, almost all of the others are going to be carbon copies of these. This is as tricky as it gets. We hardly ever have +4s and -4s in chemistry. I'll show you why real quick. If I take carbon, carbon has 4 electrons, right? Group 14. So is it going to gain 4 electrons to get 8, or is it going to lose 4 electrons to become -4? Is carbon going to be a +4 or a -4, in other words, right? Because it's exactly halfway to the octet. And what happens is, it doesn't do either. Carbon and the ones underneath carbon almost always do the covalent bonding, which we'll talk about tomorrow and Monday, okay? So carbon, I wouldn't try and trick you, is most of the time not going to form an ionic bond. Silicon, most of the time, is not going to form an ionic bond, okay? They're going to form other kinds of bonds that involve different kinds of electrons that transfer. Okay. Tonight, for homework, you've got a couple questions to answer from page 151. These are multiple choice questions, and I want them submitted through Google. So the best way to do that is to type up a little Google Doc, and 1 through 7. 1, if your answer is B, then you'll put B. The compound has the same properties as the 2 elements. Number 2, if you pick A, put A, large quantities of oxygen are trapped in the soil and rock beneath the Earth's surface. So remember, if you're giving me a multiple choice answer, please type up that answer to go with the A, B, C, or D. Make sure you click submit, and that'll be done. It shouldn't take you more than 10 minutes at the most, because all 7 of those questions are multiple choice. Jordan? No, you don't need to write the question, just as if it was handwritten. You never need to write the question. But on a multiple choice question, I want you to give me the letter and what that single answer is. Okay? And in most of these ones, it's a short sentence. One of them is 4-word sentences. One of them is short phrases. Questions?